few comments about the problem that I'm returning here. Most people had it correctly solved, but there was a group that made the same error, which means that they multiplied by inconsistent units. In other words, that problem number 2 was exercise in demonstrating the use of mass balance to find out some stream rates. And the rates were all given in pounds mass, weight, and the desired questions were also asked to be in mass rates. So in other words, if you multiply the mass of something by some concentration of a particular component, let's say in this case alcohol, well, you have to use mass or weight percentages, not mole percentages or mole fraction. It would have been correct if you'd gone to the laborious procedure of converting masses to moles, pound moles, and then multiplying by mole fraction. And then of course your answer would have been in pound moles, and then in order to exactly answer the question, you'd have had to convert back to pounds again. So that was a common error. You can't multiply by mixed units. If you multiply pounds mass, let's say of a solution, by some factor, which is let's say if it's mass fraction, it would be pounds mass of something like alcohol per pound mass of solution. And if you have the correct units, they will multiply, and they will cancel out in this indication of units that you've written alongside your numerical numbers to give you the desired units. But if you try to multiply pounds mass of a solution by mole fraction, what are you multiplying by? A mole fraction would be pound moles of alcohol in this case, divided by pound moles of solution per pound mole of solution. And they're not the same. You can't cancel that. So you got mixed units, and the answer is meaningless or incorrect. Well, I think I'll take a little time to talk briefly about dimensions and units this morning, since that came up. I'd planned to do that before, didn't get to do it systematically. But before I do that, I'll make one other comment about the problem that I asked you to work for tomorrow morning. And that is problem number 2, I guess, the last one of that set, is to be considered that we're to work out that system of vapor-liquid equilibria at 1 atmosphere total pressure. Now, maybe that was not quite clear the way the problem was stated. So in other words, the total pressure of that system is 1 atmosphere, or 760 millimeters of mercury. Okay? Well, as I just said, I thought some of the solutions to that problem suggested that maybe it'd be worthwhile taking a few minutes to discuss more or less systematically dimensions and units of measure, and a technique of converting to the desired or consistent units. Well, first of all, we sometimes distinguish, or we distinguish between the terms dimension and units of measure. Dimension is a term that describes the quantity of some physical property under consideration. So I'll write this word down. Describes the kind of a physical property. Or physical quantity under consideration. And now, then we have examples of fundamental dimensions, and I'll just write down a few. Fundamental dimensions. Examples would be volume, V, and it'd have the dimensions of length cubed. These are, excuse me, let me start over. This fundamental definitions would be length, L, and mass, M or some similar term, and time, let's say, and we could use symbol theta or T, or temperature, T. Then derived dimensions, those which are either multiples of those or combinations thereof. And for example, we have, I started to write down here, volume, which has the dimensions of length cubed, and any number of things we could write down. Velocity, small v. I intend to write a capital V here just to make it different. Which has dimensions of length or distance divided by time. And well, here's acceleration, which has dimensions of length divided by time squared, or velocity divided by time, or the rate of change of velocity. And force, which has the dimensions of mass times length divided by time squared. And area, of course, would be simply length squared, the dimensions, distance squared, and so forth. Now, the units of measure, or simply sometimes called units, refer to the term for the quantity of a dimension, quantity or size of a dimension. And we can write down some typical or units that we use for certain dimensions, such as mass. You know, we're familiar with that, mass. We use grams or pounds mass, or it could be pound moles, or it could be gram moles. And of course, length. We have in inches and feet, miles, English system, centimeters, meters, kilometers or kilometers, metric system, volume, of course. See, these are some of the terms we want to be able to, has the dimensions of, as we said, length cubed. So we'd have cubic inches, cubic feet, cubic miles, we don't use that very often, cubic centimeters, or centimeter cubed, and this kind of work, it's better to write cm cubed than it is cc, because it's clearly what it means then. Cc might stand for several things. but then we have milliliter, liter, might even say hectoliter. Hectoliter, 100 liters, the term that's used in Europe for measuring quantities in plants like wineries and distilleries, and so forth. Then, of course, we also have gallons, and, well, I wrote down cubic feet, gallons, and so forth. Well, might even put down energy or work here. Which, of course, is the product of a force acting through a distance. So it has the dimensions of mass, or time length squared divided by time squared, and of course, in other words, it's force times distance. And some of the units of measure that we're interested in and have occasion to use would be calorie, or the kilogram calorie, or kcalorie, and foot pound, pound force, and that's where I put the F in here to indicate that the pound in this case is not a pound mass, but a pound of force. And finally, British thermal unit. Or commonly abbreviated BTU. It's the system comparable to calorie in the British thermal units in the English system. And of course, we have a lot of other units. Electrical units, watts, kilowatts, and so forth, and horsepower hours, horsepower acting for an hour, things like that. So we might finally write down a few units of power, the rate of doing work. Which would be, have the dimensions of L squared over time divided by time cubed. So in other words, we'd have foot-pounds in the English system, foot-pounds force per second, for example. And a horsepower used in the English system, which is 550 foot-pounds per second. Foot-pounds force per second. And BTUs per hour be one we might use more often, and so on. So those are just some examples of units, some of which we may want to convert. I mean, illustrate here how you make conversions between some of these units of measurement. Well, first of all, I mean, your source of information about things, they may come from various sources, handbooks, laboratory, engineers' reports or so on, which are given various units of measure. We've already had considerable practice in possible units of measure of percent alcohol in alcohol water solutions and how to convert. Generally speaking, your laboratory you'd get out of a chemist in the laboratory would be given in the metric system, CGS system, grams or milligrams per unit volume, volume percent, or grams per 100 milliliters or something. And then you go out in the plant and they want to know how many pounds per 1,000 gallons is that. And so that you immediately got to be able to transfer, convert it. Maybe 20 years from now, there won't be as many conversions to make. Apparently, it's a considered effort to even to bring into more use the metric system in industry, and of course there's some government commissioner studying this and the ramifications, and there may be some legislation which will accelerate the conversion to metric system. And there are some companies that are sort of taking the initiative in developing this. But I would predict it'll be quite a long time before this is a sufficiently complete changeover of units to that those of us who are concerned with various industries will not have to be concerned with making some units. Even if you have an occasion to go look up some research results of 10 years previously, well, you'll probably find you'll have some units that not in the metric system. I have to remember how to do that, even if it's just for historical reasons. So, anyway, to make conversion of units is very simple if you just remember that in a equation or quantitative relationship must be measured by what we call dimensionally consistent units. And so the basis of conversion is fundamentally the definition of the unit itself, by which we can divide one side by the other, one side of the expression by the other, and come up with a factor which is simply a ratio equal to 1. And you can multiply anything in an equation by a quantity which is numerically equal to 1 without changing the value of the expression. So that's technically what we do. For example, basis of units of conversion, basis of conversion of units is the definition of a unit. For example, 12 inches equal 1 foot, or 5,280 feet equal 1 mile, or 1 pound mass is equal to 453.6 grams mass, frequently rounded off to 454. I'll put down some others here, just maybe some of which will be useful. 1 atmosphere pressure is equal to 760 millimeters of mercury, is equal to 29.92 inches of mercury. Happens to be equal to also 33.9 feet of water. In other words, you can use height of water as well as height of mercury to measure pressure. 33.9 feet of water. This happens to be at 4 degrees, at 30, that's at 39.1 degrees Fahrenheit, which is, or 3.98 degrees centigrade, the temperature at which water has maximum density, and is to which the temperature at which we usually refer when we want the numerical value of density. I might put down a couple more, and then we'll explain. And then 1 gallon, U.S. gallon, is equal to 231 cubic inches. And again, we'll write inches cubed. And 1 cubic foot happens to be 7.48 gallons. So now those are some of the relationships that are commonly needed. And so if we take any one of those, like this one, and say that and divide by the term mile as if this was an algebraic equation, we would have 5,280 feet divided by mile is numerically equal to 1, isn't it? So that's a ratio which has a numerical value of 1. So you can multiply any quantity by this term and not change the value of the expression. Or I guess I didn't write down here, 1 minute is 60 seconds. So of course 60 seconds divided by a minute is equal to 1. All right, now then, let's just take a couple of examples before we leave this subject. We want to, let's say, you want to convert. So here's an example. This will be an example now. Convert 88 feet per second. That's the velocity of 88 feet per second to miles per hour. Well, so then the procedure is to write down 88 feet per second. So now we want to multiply it by some of these unit ratios with a numerical value of 1, so as to come out with miles be the unit of measure in the numerator and hours in the denominator. So what are we going to multiply by? What shall we multiply by? Well, we've got to have something up here that has a mile in it. And so how many feet in a mile? Well, we've already said 5,280. So 1 mile divided by 5,280 feet is a ratio which is numerically 1. And if you've put the right units in, the ones you want to get rid of will cancel out, just like numbers will cancel out if they're equal. And you have, so now this would now, if we solved this out, would have converted 88 feet per second to miles per second. But we want miles per hour, so now we have to multiply by some factor which has hours in the bottom, in the denominator. And so how many seconds in an hour? Well, 60 times 60, of course, is 3,600 seconds for 1 hour. And now then the seconds are going to cancel. So the answer is 88 times 3,600, or 3,600, divided by 5,280 miles per hour, which numerically is 60.0, 60 miles per hour. So in other words, if you're making a series of unit conversions, you may need 2 or 3 or 4 or 5 even in an expression if you're going to do it all at once. If you have the proper units of if you set out, you should first of all, of course, set down the units of measure of the quantity you're going to deal with. Then the factors of conversion that you multiply by, if you put down the units of measure alongside those, you can see at a glance whether they'll cancel out or not. This avoids the very frequent error of having the right unit, but you have it upside down. You divide by it instead of multiply by it, or vice versa. Well, I'll take one more example, a little bit more complicated than this, and then we'll go on to something else. The next example is to convert 4,000 cubic centimeters to gallons. Gallons, U.S. gallons. Well, first of all, you may need some conversion units that I didn't write down here. I don't know for yet. But anyway, we write down the 4,000 centimeters cubed is what we got to start with. All right, now there's. I didn't write this down, but I could have, that 1 centimeter is equal to 2.54 inches. And so,
I just threw that out. It's a legal definition of an inch. That number is by law.
Yeah. All right. So anyway, all right, we'll multiply then by. Well, it may not be obvious why we have to put the inch in here, but if we're going to use this term 230 cubic inches in a gallon, well, then we got to get the inches into the thing. Hmm?
It doesn't equal 2.5 inches. 2.5 centimeters.
Yeah, it's a little bit different, yeah. I didn't catch what you're talking about for a moment. All right, that would have fouled up by illustration and very, very good. So anyway, so I'll go ahead and put this down. So if we multiply by the factor 1 inch, 2.54 centimeters, whole quantity cubed, we'll be able to cancel out the centimeters cubed. All right, now then we have the other term that from that over here, that a gallon is 231 inches cubed. And so now with our cubic inches cancel out. And so the answer is, multiplying this out, is 4,000 divided by 2.54 cubed divided by 231, which comes out to be 1.057 gallons. You could have used this factor here if you'd remembered that instead of 231 cubic inches. The cubic foot, 748 gallons. Then of course you introduce the feet into the system. First you could convert centimeters to inches using this term, and then 1 foot 12 inches, 1 foot divided by 12 inches is unity, and so forth. Well, if you'll practice that type of setup, it's easy to see whether the units are consistent or not. Because if they are, they'll cancel out to give you the desired answer. Yeah?
As long as we're picking on your word, it's interesting, in light of what you said about vapor pressure, that 33.9 feet of water is an experimental value and does not represent the difference in specific gravity between the mercury and the water. Because there's a vapor head on the water.
Well, that very well may be. That very well may be.
Temperature has to be fine Q quality, not only the specific gravity, but the vapor pressure.
Well, for my purposes, I merely took these units of conversion out of the handbook of unit values. And I don't know, and it's true that some of them have more fundamental meanings than others, yeah. But anyway. Anyway, so be it. Okay, now I had another point I wanted to finish up that I was talking about the end of the last period, and that had to do with the behavior of a component in the presence of some other component in which it's essentially immiscible, or what we have called steam distillation. The principal steam distillation, in this case where water is one of the components. And so I had developed that equation which gave the ratio between the mass of a component distilling and that of another one, such as water, in terms of the vapor pressures of the pure components. And so you can easily take two substances, and if you can decide or know beforehand that they're essentially immiscible and have access to the vapor pressures as a function of temperature, you can calculate not only what the boiling point of the mixture will be if it's treated as a binary mixture, but also the composition of it, of the azeotrope, the heterogeneous azeotrope. And I started to sketch on the board just how you'd arrive at that. But I'll do it hopefully a little bit more clearly. So in other words, let's say this is a system of normal octanol. In other words, a straight chain alcohol with 8 carbon atoms and water. And I said that if we want to find what the temperature is at which the sum of the vapor pressures of the two components acting independently equal the total system pressure, such as 1 atmosphere, the direct way to do it, or the obvious way to do it, is to plot the vapor pressures of each component as a function of temperature. And of course, if we're interested in 1 atmosphere pressure, we'll have, this is millimeters of mercury, we'd have 760 up here. And down here it'd be essentially, we might start at 0 or something a little above that. And I guess I didn't put down exactly the, I guess I didn't bring my sheet in, which has the numerical values here. But anyway, if we plotted the, start here at, let's say, this might be 100 degrees centigrade, 200 degrees centigrade, 300 degrees centigrade. If you plot the vapor pressure of water, and let's say this is about 50 here, say, you know, something like that. If you plot the vapor pressure of water, we know that it has to come up to 760 at 100 degrees. And at 50 degrees, I don't know exactly what it'd be. I didn't have the units on here very well. Let's say this is 700, 600. That didn't come out quite right, but let's call that then 100. So anyway, you'd have a curve that goes something like that. It goes up rather exponentially. The vapor pressure curves always go up in this shape. In other words, the vapor pressure increases as you approach, as the temperature goes up, it goes up in a exponential fashion. This would be the vapor pressure of water. Now, octanol has a high boiling point. It boils at about 165 degrees centigrade, as I recall. So that means it would, this isn't a very good scale I've chosen here, but the principle would be all right, I guess. In other words, I said it boiled at 100, and it seems like that's a little bit low. But anyway, let's assume that's correct. That is going to boil at some temperature like this. It has very low vapor pressure at 50 degrees, but anyway, it'd come up to some value like so. Let's say that's 100. I didn't draw that very good, but let's call that 165 degrees for centigrade. This would be the pressure of octanol. As a function of temperature. Plotted as a pure components. These are the values you'd find in the literature. The vapor pressure is a function of temperature. So then in order to find the pressure at which the sum equals whatever desired pressure you want, the pressure of water plus the pressure of octanol, let's say equal 1 atmosphere, millimeters of mercury, we add the two together and plot the total pressures. Graphically, you can do that. You add this distance to this distance, and you get this curve and superimposed on top of this one. So in effect, it would be this is a really exaggerated case, but it'd be up above here some way. And this would be the total pressure. Total pressure equal the pressure of the water plus the vapor pressure of octanol. And so the point at which the sum of the pressures equals the desired total pressure would be the boiling point. So this would be the boiling point of the mixture of the azeotrope. So the azeotrope would boil at a temperature which gives the total pressure equal to the desired pressure, or equal to the desired pressure, or for example, 1 atmosphere. Well, in reality, this curve is very poorly drawn, but in reality, this boiling point of octanol water, when they're at 760 millimeters of mercury, one atmosphere, is equal to 99.3 degrees centigrade. I guess I forgot to bring a sheet which gave the oh, well, here's one here. And if you take the relationship that we had before, that the the composition of octanol distilling in reference to the composition of the water distilling is in the ratio of the vapor pressures. Let's call this octanol, rather, pure vapor pressure of water. It comes out that I notice now that I wrote this down wrong. The boiling point of octanol is 195 instead of 165 in the pure state. It doesn't change the principle of it. It just makes your notes a little more messy. But anyway, if you solve this out for the mole fraction of octanol, in terms of the total, you'll find that the I've forgotten. I didn't bring in my calculated values, but the measured values as the azeotrope is 99.4 degrees centigrade and 10 weight percent octanol or 1.5 mole percent. Since it has much higher molecular weight, well, the percentage of on a weight basis is larger. Of course, this would be a heterogeneous azeotrope because the distillate would have both octanol and water, and they would be insoluble in each other, so that'd be two phases of the distillate. Unfortunately, I failed to bring in the sheet which showed the calculated values, but it's not very far from that value. So in other words, you can calculate azeotropes by, or the approximate composition of azeotropes by use of this assumption of immiscibility. Well, any questions about this? Tomorrow I'll give you a little table, which I didn't have time to reproduce this morning, which gives some basic characteristics of a series of aliphatic alcohols, starting with ethanol and up through hexanol and octanol, giving their boiling points, the boiling point of the azeotrope, the azeotropic composition, and the nature of the azeotrope, or whether there is one or not. And you can see it progresses from the first in the series. These are with the primary systems systems of the primary alcohols with water. Perhaps didn't say. The first one, methanol, was formed in no azeotrope. It forms a normal behavior system with water. But the next one, ethanol, forms an azeotrope at a fairly high percentage of the alcohol, 95%. Isopropanol forms one that also homogeneous azeotrope, but the percentage of alcohol is somewhat less. 88% on a weight basis, but only 68 on a mole basis. Then normal propanol is similar, except its alcohol concentration is a little bit less than the isopropyl. And then you get into isobutanol and normal butanol, you have the appearance of two liquid phases, or in other words, a heterogeneous azeotrope. And you can go on down through there, and so there's really no sharp demarcation line between the four systems that I've discussed. That's the one point I wanted to make by this table when I give it to you tomorrow. But you progress sort of gradually as you increase the molecular weight of a homologous series of substances like alcohols. And of course, the assumption we made in calculating the azeotrope for octanol is not strictly correct, because there is a slight solubility, and you would have and that would account for some of the slight deviations from the calculated value. Well, let's see. Now today we're going to do in the laboratory a little practice in distilling. We hope it all works out. The wine we initiated last week by crushing the grapes. It's been fermenting all week, and probably today is the first day it could have been distilled, and it might be better if it was tomorrow, but we're going to distill it anyway. I don't know, I think it's near dry or nearly dry, probably less than no more than 2 or 3/10% of sugar remaining. So each section will have the same experience, and we'll, what we did with those two lots of wines, we drew off the juice out of the tank and put them in 2 tanks of approximately equal quantity, and partly dictated by the situation there. We simply, the variation is, in one case we used Montrachet yeast, and the other one used a champagne strain. And if you had time to look at the tanks, you could see that they were somewhat different. I can pick out by looking at the fermentation which yeast it is, if I know that those are the two involved. The Montrachet has a sort of a whiter appearance and has a kind of a more of a tendency to foam on top, whereas I think champagne strain has more of a coagulated look and a little more of a yellow color, the yeast, and some of it tends to float on the top. Some of the clump yeast floats on the top. But they fermented about the same rate. I think the Montrachet was only slightly faster than the other one. And so those are 2 variations, and what we're going to do is try to operate the continuous column, pilot column, with the bulk of the wine, but we've also reserved 10 gallons of it to use with the little pot still. So we'll make out the same wine. At least this morning we'll try to get the little pot still started. One group do that. And of course I haven't gone into detail the technique used for pot distillation, or as far as that's concerned for continuous distillation. But as far as doing it in the pot still is concerned, as I indicated before, the method we'd use, and the only one we could use with that little 5-gallon pot still, is 2 successive simple distillations. So the first distillation is merely putting the wine in and distilling off the alcohol until essentially it runs free of alcohol, distilling off the vapor, and collecting all 1 fraction. So it's very simple, nothing to do except distill it and collect it. Then the next time, which we'd probably do next week, the second distillation, then we divide into 3 or 4 fractions. I do have a little write-up here that I'll let you have on operation of a continuous still. This is written up a few years ago, but they discusses some detail of procedure starting up and operating continuous column for 3 different purposes. And so, although I don't take time now to go through this, if you bring it to your laboratory session, you can follow through and see where it applies.